Okay, thank you for joining today's session delivered by me and Jacob. Yeah, my name is Liu. I come from Intel. And yeah, today I will do some sharing about the shared virtual addressing in KVM. And my colleague Jacob will introduce the changes in the IOMMU subsystem. So let me go ahead. So what's about the shared virtual addressing? So previously it's called shared virtual memory, but to avoid some conceptual confusion from the secure virtual machine, so we use the shared virtual addressing in our community discussion. In brief, shared virtual addressing means share address space between device and processor, so they can have unified address space view when doing some workload submission. So with shared virtual memory, the workload submission is much more efficient, and the programming for the programs is much more simplified than previous programming models. Yeah. So in previous time, we have IOVA, which used the IOMMU page table, but with shared virtual addressing, we just reuse the CPU page table. So the address space is shared between CPU and the device. That's why it's called shared virtual addressing. And so there requires some hardware support, like on Intel VDD, we have process address-based ID support. This is a PCIe concept, and we have first level and second level translation. This will support different usages like IOVA or SVA by different translation types. And we have different translation types like first level translation, second level translation, and nested translation. I will talk more about nested translation since we will use it to implement the virtual SVA in KVM. As you may know, we have Intel has VDD 3.0. We introduced the scalable mode. Actually, there is no conflict between SVA and the scalable IV. They are also picker, so you can use both of them. Okay, so for nested translation, it uses both first level and second level for address translation, and with first level to do the GVA to GPA translation, and the second level do the GPA to HPA translation. So we can achieve GVA to GPA and then to HPA translation. So this is the key to implement the shared virtual memory, shared virtual addressing in a virtual machine. Actually, this is not the only choice, but most vendors support nested translation for SVA usage in virtual machine. Okay, so with nested translation, this is how it looks like on Intel VDD. We have a first level, which is the guest CPU page tables, and we have VDD page tables, which is the second level page table. So with this nested translation, it is similar to the EPT table in CPU side. That's why we can achieve two-level translation even in virtualization environment. Okay, to enable SVA in VM, first we needed to have a virtual IOMMU with SVA capability. This should be a proper emulation according to vendor's specific IOMMU specifications. And this has no specific requirement for the implementation. You can either be fully emulated or VirtuIO based IOMMU. And since there is some page table owned by guest, there is a requirement for notification for the guest translation structure modifications. For Intel VDD, we have caching mode, which requires a translation, catch invalidation for any translation structure modification in software, so that we can track the translation structure changes in guest and modify it in host side. And then we will enable nested translation on physical IOMMU for given PASID. As Kevin session mentioned, in scalar mode, all the translation tables are per PASID granularity. Okay, so here is what the SVA architecture look like in KVM. We have multiple modules affected to introduce this functionality, like QEMU. We will have emulation logicals in the QEMU side, and we will have VFIO to program host IOMMU via the VFIO interfaces. And also we have some new APIs exposed to VFIO in IOMMU driver. Okay, so to enable SVA usage in operating system, first we need to bind a PASID. On VTD, we will bind the guest CPU page table when it's in virtualization environment, and it will be forwarded to VFIO and then programmed to host IOMMU driver, so that the guest page table will be programmed to the host side. Second, since the guest owns the CPU page table, so there is some catch invalidation to the according to the guest CPU page table. We need to forward such kind of invalidation to hoster, so that the hoster can do catch invalidation and keep the catch be the latest version. Third is since there may be some page fault during the translation in hardware side, the hardware may receive some page fault from the device side, but sometimes the host cannot address such page fault, since some, like the guest CPU page table is in guest side. So we need to report it to user space, like QEMU, the virtual IOMMU emulation device model, and then inject it to guest, so that the guest IOMMU driver can receive it and address the page request. And after the page request is addressed, it will send the page response, and such kind of page response will be forwarded to host. Then host IOMMU will send it to device. That's the whole path. Okay, so you may notice that there is some APIs between the kernel IOMMU driver and the VFIO. Actually, as I mentioned, we have no specific requirements for the virtual IOMMU implementation. It can both emulated or virtual-based. So our API will also be common for both implementation. And my colleague Jacob will mention more about such kind of converge between different implementations. So we have changes to the QEMU, VFIO, and IOMMU. So QEMU is doing the virtual IOMMU emulation and capture the guest IOMMU translation modifications and program to host. And for VFIO, we will have some new I/O controls like bind process, bind guest page table, and bind guest PASID table, and SVA invalidation to invalidate TLB for guest, and like the fault FD set. This is used for event notification, like the PRQ and the fault. And we also have the get DMA for the information to get the photo data from kernel space to user space. Yeah, for the IOMMU driver change, I will leave it to Jacob to have much more detail. So currently, I am working on the QEMU side. Current status is we have two parts. Like first is the VIOMMU emulation. The earliest VSVA API is 2017 April. This is delayed because we have some specification change. Like Kevin mentioned, we needed to do new emulation for scalable mode. So that's why it's a long time ago for the first RFC. And the second is the notification framework between the VIOMMU device model and the VFIO within Qemu. I have sent this in V3 in this April and I have some proposal to PCI SVA Ops. And also there's some work from Eric Order. He is also working on the VIOMMU work for ARM platform. He has his version 2, and we share some notification framework. So next step, we will do some consolidation for the common part. And for the there is another thing is hardware IOMMU capability query interface. Actually, this part is not included in our first RFC patch, but we have a plan on it. We will include it in our next patch set to make it sync with the host before report some specific IOMMU capabilities to the guest. Okay, I think I can leave the remaining time to my colleague Jacob. Yeah.
Hello. So for the next few slides, I'm trying to give you a brief update of the upstream status. You know, this is a joint effort between Yi and I, and also from our friends from Red Hat and John from ARM. Maybe not so friends, but anyway. So we have two tracks. So we have basically the native SVA enabling done by Zhang, and the IOMMU, the virtualized SVA from our patch set, and also from Eric Alger. So if you get all excited about my previous slides and trying to read about the slides, I'm sure you'll get confused pretty soon, because we have some really interesting terminology translation has to be done here. So on the left-hand side is the VTD. So we have some really identical concepts, but a different name. So I'm trying here to balance it out. And so on the left-hand side is the VTD, we call it PASID, and on the SMU is called a stream ID, and PASID table, of course, contains all the passes, but on the SMU is called a content descriptor table. Stage 1 is level 1, stage 2 is level 2, and all this can go on. We can go through later, but sometimes it gets even worse when you try to be nice to each other and use the other side of the terminology. But that should be all settled down after time. Since we're short on time, I'll try to do a little bit comparison of the kind of the differences between two SVA implementations. First of all, is the PASID allocation in the guest. On the VTD side, PASID allocation is global. Even for a guest, the only way to allocate PASID is through the virtual command interface and exposed through the virtual IOMMU. But on the SMU side, will be it's solely owned by the guest. Similar for the PASID table, and on the VTD side, the PASID table is shadowed. PASID is managed by the host, and the guest is shadowed. Where the SMU side, the PASID table is owned by a guest. It's only the PASID table pointer, the GPA is bind to the physical IOMMU. And the PASID, the HPA to GPA, the second level translation we have a per PASID base, like Kevin mentioned, in the scalable IOV mode, and where the SMU is basically per device and per stream ID, and all the context descriptor share the same PASID second level. So PASID 0 has a special meaning for SMMU that's used for requests without PASID, where in VTD we have a little bit more flexibility. You can use the read to PASID field in the device context table to program which PASID you want to use for handling requests without PASID. So we both support page request and response, so we can handle IO page faults. But we also both kind of diverge from the standard PCI page request a little bit. On the Intel side, we have some private data that needs response. On the ARM side, we have the stall model and some not ATS compliant interface. So I think the IOMMU domain is more the difference between the not the main difference between the two architectures, but rather the state of the two drivers. But we're working on to bring them to the same behavior. Just for VTD specifically, we try to support the default domain, which support the DMA mapping or mapping API instead of using a private domain. So this diagram tries to visualize the upstream status and the interdependencies. We don't have to go through all the components, but the color coding here is the blue for Intel, green for ARM, and the red for Red Hat, of course. And so those are the components that we have some shared components like device faults, and also individual components for the virtualized and the native SVA. I'm not going to go through all this the API table here, but those reflects in the previous patch set. If you have chance to read through it and follow the discussion, perhaps also contribute, those are the things you can look for in the first place. I think we're a little bit running out of time, so I'll just go to the summary. And so we will talk about as shared virtual address has become a convenient and efficient way to submit workload to some, for example, accelerators, and really simplify the programming model. And VTD has introduced a new spec that has a scalable mode, which is the only mode that supports PASID and shared virtual addressing. And where Yi has also mentioned the entire stack for the enabling work that's including IOMMU driver, VFIO, Qemu, and all the way to the guest counterparts. And our API design is cross architecture and also across virtual IOMMU solutions, including PV and fully emulated API. So now we have, I don't know, have time for questions, but I'll be around.
So yes. For page faults, two small questions. One is whether you are then hearing from PCI hardware vendors, card vendors, that they plan to add cards with support for that interface. And second, I guessing that for cards that do have it, right, we could get rid of the CM bit and only send updates when we are invalidating page table entries.
And you talk about the caching mode?
Yes.
You can talk about the caching, but page request is a standard PCI specification, and I don't know exactly which vendor supports it. Yeah, it's been there for a while.
Page request should be a standard concept in PCI Express, and yeah, so far in market maybe there is little device has supported it, but Intel has planned to have more IPs support the page request interface. And in regards to the question to caching mode is actually requires software to do explicit invalidation when there is any change to the translation structure, because host needs to know guest's changes and map it to host's mapping structures. That's why we need the caching mode. But caching mode is not the only choice. Other vendors may have different, but caching mode is just Intel's choice.
Thank you.
No problem. Any other questions? Yeah, it's welcome.
Thank you for your time.
Yeah. Thank you for your time. Yeah.